Good morning, everyone, and welcome to International Workshop on Translating Glass Science into Technology. Akal University was established in 2015 with an aim to provide up-to-date and world-class scientific education and moral values to our young minds. So continuing that trend, we usually organize such events. And now when United Nations has declared this year as International Year of Glass, we decided to celebrate it in the form of a one-day workshop. So that's how this workshop was organized. And for today's workshop, we have three speakers. Dr. Ashutosh Goel, Associate Professor at Rutgers University, USA. Dr. Kulvinder Kaur, Marie Curie Fellow at Royal College of Surgeons, Ireland. They are with us right now. And our third speaker, Dr. Saurabh Kapoor, who is a glass scientist at Sterlite Technologies, Aurangabad, will join us online mode. So on the behalf of Akal University and all the participants, I welcome our speakers. I also welcome our respected Dean Academic Affairs, Professor G.S. Lambaji, for sparing his valuable time for today's event. He has also joined us here. And now today's event is divided into two sessions. In the first session, we have two speakers. Then there will be a lunch break from 12:30 to 1:30. And then at 1:30, we'll start again with our third speaker. And after his talk, there will be a panel discussion in which the participants can ask their question and queries to the speakers. And then there will be a formal vote of thanks. And the workshop will end up by presenting a mementos to the speakers. Now I request Professor G.S. Lambaji to please come over here and say a few words about the workshop.
Very good morning. I welcome you, especially our respected resource persons, Dr. Goel and Dr. Kulvinder Kaur, to the Akal University for this occasion of celebrating the International Year of Glass, which the UN has declared with the aim of saying that to shine a light on the role of glass in our societies and show how technology like glass can contribute to a sustainable development. The key word is sustainable development, and how technology can play a role in use of glass towards sustainable development. Every year UN chooses several topics which become a focus area for that year. In this year, the topics are glass and artisanal fishery. The spotlight on glass is meant to highlight how a traditional product can be a product of sustainable development. I'll request the participants to mute their mics, please. Humans have been using glass for thousands of years. Today, glass is an important part of our lives. We use glass to build cars, aeroplanes, houses, sculptures. We use it to communicate at the speed of light with the fibers in our internet cables. We use glass to see more with microscopic lenses and to save energy with insulation. Glass production is a good example of the progress that has been made in decades and centuries, considering energy consumption and emission, and of the need for a sustainable use of resources like sand. As far as this workshop is considered, in the beginning of our new session, we are conducting this workshop. Our Akal University is organizing this one-day international workshop on translating glass science into technology to celebrate the International Year of Glass. We have about 100 plus participants. Since the students are presently on leave and would be joining us by first week of August, they are connected online, and most of our faculty members are available here offline. I won't like to take much time to introduce our respected speakers of the day. As the coordinator just introduced that Dr. Ashutosh Goyal is the associate professor at the Rutgers University, USA, and Dr. Kulwinder Kaur, she is a Marie Curie fellow at RCSI University of Medicine and Health Sciences, Ireland. And we are privileged that both these speakers are physically available with us here. I am sure that the audience today are going to find it really very intriguing and encouraging to find intricacies of the technologies in glass. To a layman, glass may not communicate the amount of usage of glass in technology, but to learned people, I'm sure this would make much better sense. So be open to interact and clarify your gray areas with the users. Of course, after the three speakers have presented their thought process, we are having a panel discussion with them to clarify any common doubts. I'm sure you would be wide awake and listen to their ideas, their wisdom, because they are experts in this particular field. Once again, I thank our respected speakers to spare time and be with us here, and also to all the participants, expecting that they would be drawing the maximum benefit of this workshop today. Thank you very much. Wish you all the best.
Sir, speaker is not audible.
I'm sorry. I'll repeat it, please. So Dr. Goyal has received his bachelor's and master's in physics from Guru Nanak Dev University, Amritsar, and PhD from University of Aveiro, Portugal in the year 2009. He joined the Department of Material Science and Engineering, Rutgers University in the year 2014. Before joining Rutgers, he was the material scientist at Pacific Northwest National Laboratory, USA, and a senior research scientist for optical fibers at Sterlite Technologies, India. Dr. Goel's research is focused on understanding composition structure property relationships in oxide glasses. He has published more than 90 papers and has 2 US patents on his name. He is associate editor of Journal of American Ceramic Society, International Journal of Applied Glass Science, Frontiers in Material. He is the editorial board member of the journals Ceramics and Materials. Dr. Goel is a chairperson of the Technical Committee on Hazardous Waste Vitrification and a member of Technical Committee on Glasses in Healthcare of the International Commission on Glass. He is the Vice President of Bioceramic Division of American Ceramic Society. Due to his outstanding accomplishments, he has been awarded 2017 Vittorio Gottardi Prize by International Commission on Glass, and in the year 2021, he was awarded W.H. Zakariasen Award by the Journal of Non-Crystalline Solids. Now I request Dr. Goel to please deliver his today's talk.
Hello, everyone. A very good morning. I hope I'm audible to everyone. First of all, thank you very much for having me here. It's a pleasure, and thank you, Dr. Lamba, for inviting us over here. It's as Dr. Lamba also said, and Rajan also said, it's 2022 has been declared as the International Year of Glass by the United Nations. So it's a series of events that are being organized around the world, like from July 1 to July 9, I was in Berlin, Germany, talking about this, like on the same stuff, kind of like it was an international congress on glass. So such events are being organized all around the world this year. And I'm glad that Akal University took an initiative in this aspect and, being a part of it, which actually brings your university on the world map, global world map, at least in the field of glass research. So what I'll be talking about today is a bit of what we do in my lab, and I'll try not to bore you with a lot of data. So if you please feel sleepy, raise your hand and I'll make sure you find it interesting, whatever you have. And then you don't have to stick to English to talk to me or something. Even if you want to talk to me in Punjabi or in Hindi, feel comfortable about that. Like किसी भी language दो बच्चों बोल सकता हूँ, कोई problem नहीं है. All right. So turning nuclear waste into glass in the US, a brief overview. Before I move ahead, it's a customary slide. We need to acknowledge our funding agencies who have supported my travel and all the research that whatsoever we do there. And the research in this case has been actually funded by US Department of Energy. So, thanks to them. And then I'll start with the story of the very first nuclear bomb or the nuclear weapon that humans ever made. So we know India has a nuclear power, right? We have nuclear weapons, and United States was the first one to produce the nuclear weapons. We also know that, but how did that actually come into existence? So it all started way back in 1933. You must have heard about the name of Dr. Enrico Fermi, Fermi Lab, right? MSc students padhte hain iske bare mein. So Enrico Fermi, so it was actually Leo Szilard. He conceived the idea of nuclear chain reaction, that we can control the nuclear chain reaction in the form of nuclear reactor. And in 1934, Leo Szilard and Enrico Fermi actually filed the very first patent for a nuclear reactor, that we can control this chain reaction in the form of a nuclear reactor. Now, once they filed this patent, and this was a time when Second World War, or Germany was, like Hitler was in Germany and he wanted to occupy the whole Europe and probably the whole world. And that's where, at that time, Hitler had just occupied Czechoslovakia. Today, there are two countries, Czech Republic and Slovakia. At that time, it was Czechoslovakia. And Czechoslovakia is actually a source of uranium. They have uranium mines. So most of the uranium around the world, and even in today's date, comes either from that region of Europe or from Canada. Okay, Canada have a lot of uranium there. So Czechoslovakia was the source of uranium, and all of a sudden what they realized is that as soon as Germany occupied Czechoslovakia, Hitler occupied Czechoslovakia, the uranium outsource from Czechoslovakia stopped. Now they were worried that it is a possibility that Hitler is probably trying to somehow replicate the US research and create a nuclear bomb. And if that happens, it will be a disaster. So what Enrico Fermi and Ziller did, they went to Albert Einstein. We know all Albert Einstein, right? They went to Albert Einstein. He was a professor at Princeton University in New Jersey at that time. In fact, Albert Einstein's house is just 20 minutes from my house. It's in New Jersey, So he was a professor there at Princeton University at that time. And these guys, they went to Albert Einstein and said, see, president is not going to listen to us. We are small guys, but you are the Albert Einstein. Why don't you write a letter to the US president and request him to start funding the projects on making nuclear weapon for the US? Because if in case Germany succeeds in making a nuclear weapon, it will be a disaster, right? So this is the copy of the letter, actually what Albert Einstein did not actually write the letter. The letter was written by these two gentlemen. He just signed it, right? Most of your recommendation letters. He signed it. So Albert Einstein there, and the letter was addressed to the President Roosevelt at that time. So with this letter, when President Roosevelt read this letter, he got shocked and he immediately approved Manhattan Project, the very famous Manhattan Project, which led to the development of the first atomic weapon, Little Boy and Fat Man. Okay, so these were two weapons, two atomic bombs that were dropped in Japan, Hiroshima, Nagasaki, Little Boy and Fat Man. Little Boy was dropped on Hiroshima, Fat Man was dropped on Nagasaki. Okay, in 1945. When they dropped and everything, and then they, World War II ended, and they occupied Germany, they freed from Hitler. Hitler was killed and everything done. Then they realized Germany could never actually copy their research. Germany was nowhere close to making an atomic bomb. And by the time Einstein was in his deathbed, he actually said, the only regret that I have in my life is that I signed that letter. Have I not signed that letter, probably the world would not have got so dangerous. But okay, that's history. Now, where do we come into here? And I usually tell my students when they work on this for their PhDs or postdocs, like your professor, Dr. Rajan Saini here, that you guys have a legacy with Einstein, because something that he started with something that started with his signatures. Now, we are still continuing to work on that. So atomic bombs were made, right? Atomic bombs were made. So this is the site where plutonium was extracted for the Fat Man bomb. This is the nuclear reactor, actually. It's called B reactor. This is the nuclear reactor where the plutonium was extracted to make the Fat Man bomb, which was dropped on Nagasaki in 1945. After that, United States produced thousands of atomic weapons. In today's date, as per 2021, US has more than 3,000 nuclear weapons, right? Active nuclear weapons. And all we know is that yes, nuclear weapons are being produced, and India is now a nuclear power, or US is a nuclear power, the biggest nuclear power and whatnot. What we don't realize is when these nuclear weapons are being produced, right? Whatsoever is left out of the nuclear reactor comes out of the nuclear reactor. Whatever comes out of this nuclear reactor is actually a waste now. And it is not only a simple waste, it's a chemical waste, it's a radioactive waste, which you cannot just throw it out, dump it out in somewhere, landfill or something like that, right? So you need to take care of it, correct? And in the US, just at one site called Hanford site, where during this nuclear weapon proliferation from 1940s, like the World War second time until 1988, that was the Cold War era with Russia, USSR at that time, the fall of Berlin Wall, right, in Germany and everything. United States had produced a lot of nuclear weapons, which resulted in actually production of 55 million gallons of radioactive waste. 1 gallon is 3.7 liters. In India, we talk in liters, right? 3.7 liters multiplied by 55 million. 1 million is 10 lakh, right? So you can imagine the amount of radioactive waste we are talking about, and that's only one site in the United States. Of course, this is the largest site in the US. There are other sites which have radioactive waste, but it's small in amount, not in this huge concentration. And this waste has been stored in 177 underground steel tanks, and each tank is probably bigger than this room. All right. So 177 such steel tanks, underground steel tanks, were made in which all this radioactive waste was dumped in there. And it was until 1988, it was being done. So in 1988, they ceased the production of plutonium. In 1989, they started the cleanup. That we are done, we don't want anything else, right? Let's now start cleaning up the mess what we have created. But now what do we do? What do we do with all this? And then is really this waste dangerous? Just to give you a perspective, of course, we all know nuclear waste is dangerous. But just to give you a perspective of how and why, what are we talking about? When you throw a paper, like, we throw a paper in the bin all the time, right? Every day. It takes about a month for that paper to decompose. If you put it into a landfill, it'll take a month to decompose. If you throw an apple's core, it takes around 6 months to decay. A plastic cup, 500 years. Nuclear waste, sometimes millions of years. And then above that, it is radioactive, right? And it can cause a lot of damage. Like, think about what happened in Japan, right? Fukushima disaster. Radioactive iodine, iodine 129 is an isotope of iodine. It leaked into Pacific Ocean. It went into the flora and fauna in the ocean. United States was worried because US shares from the California. California is on the bank of Pacific, and on the other hand, it's Japan, right? So US had their scientists posted on the bank of Pacific just to make sure they were checking the radioactivity of Pacific from time to time, just to make sure that no radioactive elements or isotopes are being, or no radioactivity is being actually, transported from Japan to the US through Pacific, right? Also, what I'm trying to say over here is a lot of these radioactive species are water soluble, which we don't even realize. Iodine 129 is highly water soluble. It is not highly radioactive, but its half-life is in millions of years. It enters your body through flora and fauna. Somebody eats fish. If that fish is caught from Pacific, it enters your body. Now, you won't even realize, and slowly and eventually you start getting all those diseases, right? Just to give you an example, a perspective of it. So now, what do we do with this waste? Can we leave this waste in the tanks forever? You don't want to leave this waste for your next generation, right? At least I don't want, I have 2 kids. I don't want my kids to have this issue, this problem going on forever. So what do we do? One question that I get all the time, especially from students, is can we shoot this waste to sun? At least in the US, whenever I give such a talk, students especially come to me and they'll have, not only students, I was at Delhi Public School 1 week back. I'll be talking at Delhi Public School day after tomorrow on Wednesday in Rajpura, where I belong to actually. So the principal of that school asked me, Dr. Goel, can we shoot this to sun? And I was like, I'll discuss that once I'm there. But no, it's a really good idea. But think about it. Even the slightest possibility of failure will lead to all these millions of gallons of waste spread all over the earth. Do you want that? No, we don't want, right? So again, what do we do out of it? That's where it is. Let's turn this waste into glass. And I'm not saying to get a bottle of glass and then put the waste into it and seal it. Let's make glass out of it. Let's turn this waste into glass, right? I'll show you in a minute the composition of this waste on a periodic table, and then probably you'll get a better idea of what I mean. But so why glass? To start with, glass has a highly flexible structure. Do you know Mother Earth, Mother Nature produces glass all the time, right? So for example, your volcanoes, lava. When the lava comes out of a volcano, and if it cools down slowly, what does it form? Igneous rocks, right? But if it cools down rapidly, think about Hawaii. You must have heard about Hawaii, right? It's an island of the United States. Hawaii is in the middle of Pacific Ocean, and there are a lot of volcanoes over there. When the volcanoes burst out lava, the lava actually enters into Pacific Ocean, and as soon as it enters into Pacific Ocean, it freezes and turns into glass. So if you allow the melt to cool down slowly, it will turn into crystal. That's called rock. If you cool it down really fast, it turns into glass. Okay. And it can accommodate anything into its structure. You can think about, that's why I gave this example of volcano over here, because volcano, it's a natural thing. It will have all the elements, whatever present in the Earth's crust, right? And all of these can be accommodated into the glass structure, in the structure of glass. Glass is durable. Do you see, the best example is your windows around you. Do you have to replace your windows every year? No. Once you install the windows, they're good for decades, correct? So glass is durable. And then the whole, let's say if the tank is this big of a room, right, size of a room, this can be actually accommodated into this big piece of a glass. The whole, the waste, which is equivalent to this, in this room, the volume of this room, when it's converted to glass, it can be actually shrunk into a form of a piece of a solid, which is this big. So you can easily handle it, easily store it, and easily take care of it. That's why the scientists chose glass. So now the current strategy, and whatever I'm talking about here, it also applies to the Indian scenario. In India also, we are doing the same thing. Okay, Bhabha Atomic Research Center, Trombe, or IGCAR Kalpakkam, they're doing the same thing here also. So what happens is the waste from the tanks, I showed you 177 underground tanks, right? Those, the waste from those tanks is pumped into a facility called pre-treatment facility, in where they divide this waste into two waste streams, depending upon the radioactivity of the waste or the composition that's coming out. Something is called, one is called high level waste, another is called low activity waste. And you can understand from the terms itself, high level, it has got some species which are highly radioactive. Like for example, it may have some cesium 130, strontium 90, uranium or something, they have already extracted it out. We are not worried about those. Okay. When I say low activity, means there are ions or there are radioactive species which are low in activity, but the problem is they have millions of years of half-life, like iodine 129, technetium 99. They are water soluble. They have half-life of millions of years. If they enter into your food chain, again, it's a big problem. Okay. So it goes into this pre-treatment facility. And when it goes into this pre-treatment facility, divided into two, high-level waste and low-activity waste. And then when from there, it is sent to the melters. The melters are huge. And this waste is mixed with the components like sand, reta, sand, right? Silica, and calcium oxide, like your limestone, for example, sand, limestone, boric acid. They mix it with these components and then melt it at around 1150 degrees C, 1150 to 1200 degrees C to convert it into glass. And then this glass is poured, this melt is poured into these steel canisters and shipped to repository, wherever it has to be stored. High level waste will go to some geological repository. When I say geological repository, think about something like a barren land somewhere, like let's say we go to somewhere in Rajasthan where it's all deserts, for example, and then you start digging it underground over there. You make a whole repository there and then store those, steel canisters over there, basically where you do not expect mankind to go and live over there, and the environment around is conducive for this. ज़्यादा बारिश नहीं पड़ती है या कुछ नहीं, so that there is no lot of moisture, not a lot of corrosion or anything, where it will stay safe for years and years and years. And we are talking about thousands of years in this case, right? Now, here the US Department of Energy is building up a 67 acres of this glass vitrification plant in the area of 67 acres. In Indian terms, if you talk about it, we all watch cricket, right? Do you know the area of cricket ground approximately in acres? One international cricket ground is 4 acres. Think about 67 acres. 17 cricket grounds, almost equivalent to this glass vitrification plant. This this unit which is being built over there with an investment of more than $17 billion. This is the world's largest glass manufacturing unit. Well, I won't say glass manufacturing unit, waste treatment plant, where they'll convert this radioactive waste to glass. Okay, and it is supposed to start this year, sometime by the end of this year, most likely. So, to summarize, so far, plutonium extraction ceased, cleanup began, and the glass is going to be made in 2022. It's going to start in 2022, and it will go for next 20 or 30 years. It's that much of waste that it'll continuously work for next 20 to 30 years to convert all this waste to glass, right? So what's the problem? Why am I still standing here and giving a talk? Or why are we spending, why the government is spending their money and we are spending our time and effort doing research on this topic when everything is going to end, right? Logical question here. 2022 में सब शुरू हो रहा है, सब खत्म हो गया है, glass बनना शुरू हो गया. So why are we still working on this topic? The problem comes here. In the United States, what we always talk about, that research comes out from taxpayers' money, right? If the people won't pay tax, we won't be able to get funding for research. So there comes the part of accountability. Similarly, in this case also, the building of this nuclear waste vitrification plant, waste treatment plant, as well as for the life of the mission, let's say if this mission works for 30 years, goes in for 30 years, right? It will cost government another billion or trillions of dollars. Manpower, electricity, all the infrastructure, breakdown, maintenance, repairs, everything, right? Assuming, let's say if this mission have to go for 30 years, can we somehow design the glass composition in such a way that they can accommodate, if they are accommodating today X% of waste per 100 grams of glass, right? Can we make it X plus delta X? Can we increase that waste loading so that per 100 grams of glass or per kilo of glass, we can have extra waste go into it without compromising with the performance of the glass, without compromising with the performance. So when I say performance, it's the chemical durability, because you do not want the glass to corrode easily and then degrade out everything, release everything, right? So that's where it is, because even if we can save 10 years in the mission of this waste treatment plant operation, it's going to cover up all the cost of R&D, because government is going to save billions of dollars on this, right? So that's where we come in. And now, just to give you an example of how a nuclear waste looks like, the composition of a nuclear waste, I usually joke with my students, throw a dart on the periodic table, wherever it hits, that element is in the nuclear waste. It's almost rich in everything, in every series, like you can imagine all the red color items elements that you see, they are actually present in the nuclear waste in different concentrations. The green ones that you see here, we add them before it goes into the glass melter. Okay. Sulfur, I put it in yellow because it is not present in the high level waste, or it was not supposed to be present in the high level waste earlier, but now it is expected that it will also come into high level waste due to some reasons, which I don't want to go here. But so you can imagine, like, it's a pretty complex system. Usually scientists like to work with 2 or 3 component materials, simple, so that they can understand the fundamentals of it. Whenever you are taught in the classroom, you will be taught with the simplest example possible, right? That's the same with fundamental science. We always love to work with the simple system so that we can explore the fundamental science. But in this case, we are talking about technology, translating science to technology. And so from those 2 or 3 component system, how do we convert that science to such a huge multi-component system? That's technology, right? So now, when the system is such complex, you can imagine there will be several problems associated with it. So the first problem that comes in, now think about it, waste is coming in. Think about, like, you must be having those, in India, it's pretty common, at least at my house, we have it here, that you have a motor which pumps the water up to the tank, something of that sort, right? Think about the same way if there is a motor which is pumping all the radioactive waste into the melter, right? Radioactive waste is liquid, semi-solid, semi-liquid form. It is being pumped into the glass melter, and now it is being melted over here. And due to some reason, electricity went off. Power cut lag gaya, Punjab government ka light chali gayi. Right? Now what do? The melter was running at 1150 degrees C, right? All of a sudden the temperature started to fall down. This condition in this case is called idling, melter idling. Now, if the melter is in idling state, the temperature is falling down rapidly from 1150 degrees C to 800, 900 degrees C, 950 degrees C. In this case, what happens is, I'm assuming you guys know the concept of liquid of temperature. In the phase diagrams, if you talk about phase diagrams, we have got alpha solid, remember alpha plus L, and then L. And the boundary that differentiates between alpha plus L and L, that's called liquidus line, right? So when the melt is cooling down from liquid state, from L to alpha plus L, when it crosses that line, that's called liquidus temperature. So when the temperature is falling down, right? Think about this is L, liquid. When it's cooling down, the temperature is falling down. It crosses that line alpha plus L. And now all of a sudden you have a mixture of alpha and L, solid and liquid. That solid usually comes out in the form of spinels. You know, spinel crystals, right? MgAl2O4 kind of stuff. So in this case, what we are talking about is spinels which are rich in iron, nickel, manganese, like all these transition metal cations. The density of these spinels is around 4 gram per cc, 5 gram per cc. So what I'm trying to say over here, if the density is higher than the melt itself, the density of melt. So what will happen if the density of the crystal is higher than that of the melt? They'll settle down, right? Now, even if you, let's say electricity came back, power cut is done, electricity came back, and you started to heat the melter again. Now these crystals, they'll not melt. They'll stay there. Not only they'll stay there, they'll also deposit in the spout. Spout means the mouth of the melter, right? So once they start to form over here, what will happen? It will block. So now the melter cannot work properly. It cannot throw out the melt, or it cannot, once the waste has been converted to melt, it cannot be poured out, obstructing the flow of the melt. That's one problem. That's called spinel crystallization in glass melter, right? So one of my PhD students, she got a PhD on this topic. Now, I was just talking to a student here. She'll be joining Corning. If you know Corning, it's a company which makes the iPhone screen of your iPhones, or Samsung phones. Gorilla Glass, if you know Gorilla Glass. It's the world's largest company. She'll be joining there as a glass scientist in August. So now somebody over there, when an engineer basically came up with a constraint saying that if we design the glass composition in such a way, and it's a hypothetical thing, like, somebody came up with a random idea, no scientific logic to it, that if we design the glass composition in such a way that when it's cooling down, when the melter is cooling down, if we do not allow the amount of crystals to be more than 1%, right? From X-ray diffraction, you can calculate the amount of crystals in your solid material. So what they said is, if we do not allow the spinels to form more than 1%, we can somehow stop this problem. So they made it a constraint and they implemented it. But further research figured out that this is actually not true. This is highly empirical. किसी ने धक्के से बना दिया और वो चल रहा है. Right? There is no scientific basis to it. What they figured out is, if we can increase this crystal tolerance to 2% or to 3%, if we can allow the crystals to form to 2% or 3%, we can reduce the amount of glass that we need to produce considerably. The 30 years mission can be actually wrapped up in 25 years or in 20 years. It will reduce the cost of the mission. But then how do we do that? That's where the challenge comes in. I won't go to, there's another constraint, but I won't go to that constraint. So basically what now the national labs are doing, they want to develop a predictive model This is a huge thing in today's date in the field of research, predictive modeling. Instead of making an experiment, can you use artificial intelligence? Can you use machine learning? Can you use simulations to predict what kind of behavior you are expecting from a material? Right? That's a huge thing. A lot of times I receive requests from industry saying that, hey, Ashutosh, either we get students who are trained in material science, or we get students who are trained in artificial intelligence, computers, machine learning, but we don't get someone with a background in material science and trained in artificial intelligence, or vice versa. Can you guys produce those kind of students? So that's something for the students over here at LIFT you may want to think about for your future research careers. It's a huge job opportunity, huge demand in the market today, and it will stay for another decade at least. So predictive models are being proposed, but then these predictive models, they need a lot of data. Machine learning needs a lot of data, right? Predictive models need a lot of data. And if you want to not only, and machine learning is highly empirical again, if you want to club science with machine learning, you need simulations. If you need simulations, you need experimental data for that to validate the simulations, right? So you need fundamental science and a lot of data to reach to a level where predictive modeling can be done. That's where we come in. That's the kind of research we do. I'm an experimentalist, right? And we do a lot of fundamental science on these kind of compositions. How does the atomic structure of a material control its properties, macroscopic properties, from molecular level to the macroscopic level? How do we connect the dots? That's the kind of research we do. That's one. Second problem. Now imagine you somehow circumvented this problem, solved this problem, and now you poured the melt into a steel canister, right? Crystals की जो problem थी आपकी जो deposition की spinels की, वो आपने उसको avoid कर लिया, and now everything went fine. And now you poured the melt into a steel canister. When you're putting the melt into a steel canister, can I play this video please here? If you click here. So that's fine. That's fine. So it's a video over here, and I was worried about that if this video will work over here or not. At least it works on my laptop. But so think about it in the form of a. Can I get a water bottle, please? Anything? Yeah. Think about it like this is a steel canister, right? If this is a steel canister and the melt is coming from the top and getting poured into it, like the way water bottle is filled, right? Melt is at 1200 degrees C, and the bottle is empty, the canister is empty. As soon as it comes in, as soon as it falls into the canister, the first drop of the melt will come in contact with the steel bottom, right? As soon as it comes in contact with the bottom, it's metal. Metal is good conductor of heat. It will absorb the heat. Melt will dissipate the heat. It's rapid quenching, rapid cooling. The melt will turn into glass. I told, right? Like how Mother Nature produces glass. Think about the second spout of the melt that comes in now, and it again drops in there. What will it come in contact with? It will not come in contact with the base. It will come in contact with the previous layer of glass that's lying there, right? It will come in contact with the steel on the edges, but from the bottom, it will not come in contact with the steel. Now it will come in contact with the glass that has been already deposited there. And glass is an insulator, right? It won't release heat so quickly. So slowly what will happen, layer after layer, when the glass is spout after spout, when the melt is being poured on it, the edges will cool faster because they are coming in contact with the steel. At the core of the bottle, of the tank, it will cool the slowest, right? Because it's in the center of it and everything is covered by the glass around it. So what happens is you eventually get crystallization. If you allow the lava to cool down slowly, it crystallizes, right, into igneous rock. So the same thing here. You see over here, this is an infrared imaging of the crystals being formed in the tank, or let's say a simulation of the crystals being formed into a tank, right? So when these crystals are formed, again, just need to take it by my word here that when these crystals are formed, the kind of crystals being formed over here, they are not good for the long-term performance of the nuclear waste. They reduce the chemical durability of the nuclear waste glass considerably. So your aim is to suppress the formation of these crystals. You do not want these crystals to form. You want the steel tank to look like this, steel canister to look like this, not like this. Make sense? So in order to do that, scientists have come up with, again, they've started collecting a lot of experimental data, and then they started coming with a lot of empirical models. No science, just empirical models. ऐसे करके देखते हैं, ये वाला मॉडल बनाकर देखते हैं, शायद कुछ काम कर जाए. They came up with several models, and they made, plotted all these compositions on this ternary diagram. I showed you, like, this nuclear waste composition is 25 to 30 component. There are a lot of elements from the periodic table. They normalized all of them into this ternary diagram, sodium aluminosilicate diagram. And then what they found is all these black dots, right? These are all glass compositions which do not crystallize when they are poured into the steel canister. All these red dots, diamond, Z, X, plus, whatever you see, they all crystallize. Okay. So they came up with an idea. Oh, this region does not crystallize. The composition with this region does not crystallize. Based on that, let's come up with an empirical model called Nepheline discriminator. And, we'll design our compositions based on this. But now the problem is, if we design the compositions in this way, the amount of waste that goes into the glass is really small. So that does not help. In fact, that just leads to expansion of your time and money needed for this waste treatment plant. It does not reduce it, it expands it. On the other hand, what they also figured out is there are regions where we can find compositions which do not crystallize. But then what's going on here, we don't know. Why these systems are not crystallizing or why these systems are not crystallizing. So basically what I'm trying to say over here is it's all empirical. There is no basis of science behind it. So similar way, other models were being proposed which are semi-empirical or empirical, and eventually after like 4 or 5 models being proposed, came in another model called submixture model. It was highly empirical. They collected thousands of data points and then they plotted them and figured out, okay, in this region you do not see nepheline, in this region you see this crystalline phase, will go this way and that way. No science behind this. Eventually what happens is that now we have no clue what's going on at the scientific level. All we know is, and in this case what happens is you collect 1,000 data points. Out of those 1,000 data points, 800 will go your way, the way you predict them. But there will always be some 150 or 200 data points which will deviate from your trend, because there is no science behind it. It's all empirical, and until you don't understand what's going at the fundamental level, you cannot really actually predict everything, right? So that's where we were funded to do this job, to figure out what's the science behind all of this. And at the scientific level, at the structural level, what is it that's controlling the crystallization of this phase? Because if you understand, like the way doctors say, if you know the root cause of your problem, of your disease, we can treat that. Otherwise, we'll just keep on giving you crocin or paracetamol and reducing your fever, right? So it's the same way in this field also, in the research also. If you know the root cause of the problem, only then you can tackle that thing. So that's where we were funded, to figure out what's the root cause of this problem. And we have spent, like, since 2014, we are in 2022 now, 8 years working on this. And I think we are there. It took us at least 7 years to figure this part out, but I think we are there, where now we can confidently say that, yes, we understand what is it that's required to suppress the crystallization, or what is it that leads to promotion or suppression of this phase. Now it is up to the engineers over there, scientists over there who are actually doing this job, whether they take our recommendations or not. But at least from our end, we are telling the government, the federal agencies, that this is what you need. You need to take care of this in order to solve the problem, right? So that's the kind of research we are doing there. So now let's say we came across, we figured out this part, and we designed the compositions in such a way that this crystallization problem is solved, and all the waste has been turned into glass and it's stored in the nuclear waste in the steel canisters. Now those steel canisters, this is the waste in the steel canister. It will be overpacked by different materials, like for example lead or something like radiation shielding materials, and then it will be further overpacked by bituminous coal, bentonite coal, and sand, right? And like, let's say a concrete thing, and then it will be taken to a geological repository to deposit it or to submit it over there, or to store it there. So that's the geological repository where we have dig it underground somewhere in Rajasthan or somewhere in isolated area in deserts, right? For example, just giving an example, or in mountains somewhere where nobody lives and we don't expect humanity to go there and live over there, something like that. So now, over the period of time, there will be in the soil, in the sand, in the mountains, anywhere, there is always some moisture. There are always some microorganisms, bacteria, fungus, everything, right? All these things, they'll attack. They'll start interacting, they'll start attacking this, you can say the encasement, the whole encasement, right? And they'll start reacting with it slowly, and eventually what we are expecting or what we think 1,000 years from now, all these barriers will be gone. And then the glass will be exposed to water. So now comes in the problem of chemical durability of glass, right? Now we want that the glass, even if it comes in worst case scenario, 1,000 years from now, although we won't be alive by that time, but our next generations or whosoever is alive at that time should not curse us. What the heck did we do for them, right? So can we make that glass so durable that even if it comes in contact with the water or with the moisture, groundwater, it does not really, corrode so badly that to give us all kinds of problems, right? So that's another area of research we are pretty active in, where, so like, for example, well, in India, we have here plastic bottles. I was in Germany, as I said earlier, in the first week of July, and I was surprised over there. I did not see even a single water bottle there of plastic. In the hotel where I was staying, they had all glass bottles. At the airport, they had all glass bottles, no plastic bottle. But okay, so when you have your water in a glass bottle, right? If you think it is not reacting, it is not interacting with the glass, no, that's not true. Glass always keeps on interacting with the material it is in. You store pickle, you buy pickle, right, from the market, or you buy all kinds of things from the market in the glass jars, glass containers. Depending upon the pH of that solution in it, glass is actually interacting. If you take a piece of that glass, put it under a scanning electron microscope, you will see layers after layers on the glass of the altered glass. What you call altered means reacted glass, right? So, but still it's much safer than plastic, no doubt. Having said that, so in the same way, in this case, glass is again what we want. Glass should not react, or well, glass will react, but the reactivity should not be so much that it can lead to an accident, a huge disaster at that time, where all the radionuclides, they release out of the glass and start going into the vegetation or start going into the farms and the groundwater and everything, right? So that's where a lot of research is done. Anyone over here if works in bioglass, I know probably Kulvinder works in bioglasses, you must have seen when you study the ICP profile, or when you study the elemental release profile of your glass in SBF, simulated body fluid, for example, it usually shows something like this, right? So when a glass, when you take a fresh bottle made out of a company, you put water into it, store water into it, right? As soon as you store water into it, and if you start after, let's say, few hours, every few hours, if you take 10 ml of that water from your water bottle and pass it through a technique called ICP-OES, inductively coupled plasma optical emission spectroscopy. It's a technique to measure the concentration of the elements present in the solution. If you take that sample of water every few hours and measure the concentration of elements present in the sample, just pick up anything because your water bottle is made out of soda lime silica, sodium, calcium, silica, right? Just measure the concentration of sodium, for example. You will see such a curve being formed with time, right? So what's happening over here in this phase, sodium from the glass is coming out and hydronium ions from the water are going in, H plus, sodium hydrogen exchange, ion exchange is taking place. Over here in this region, you will see a silica gel layer being formed, SiOH. Now the water that's going in will react with silica to form silicon oxygen hydrogen bond, SiOH bond, right? And then comes in this part. But long story short, this is another issue, another problem where we are working on how to make sure that the glass that we are using is highly safe for our next generations to come, right? I don't know how much time I think I'm already past the time, so I won't take. But in nutshell, these are the three big problems. I just wanted to give you an overview what we work upon. There are other stuff also. There's other stuff what we work upon, and my PhD students are working on that. But in 45 minutes, whatever I could cover is that this is the summary over here, that there's a huge problem of nuclear waste, and it's all over the world. It's not only in the United States, it's in India, it's in China. China is getting huge nuclear reactors. They're building nuclear reactor after nuclear reactor. In the future, the problem will come with your solar panels. You're producing a lot of glass with solar panels. A real recent problem that's going to show up is your mobile phones. How to dispose of all the plastic, how to dispose of all the toxic elements present in your mobile phones, right? We don't think about that, but waste management is a huge problem. We need to think about that. If we only talk about greenhouse, we only talk about global warming, but this is another aspect of environment we barely talk about. We need to start to talk about that. With that, thank you very much.
So the questions will be asked in the panel discussion. So thank you, Professor Goel, for such a wonderful and informative talk. Now I introduce our next speaker, Dr. Kulvinder Kaur. Dr. Kulvinder Kaur received her master's in physics with gold medal from Guru Nanak Dev University, India. She received her PhD from the same institute with Inspire Fellowship. Presently, she is Marie Curie Fellow at Royal College of Surgeons, Ireland, in the research group of Professor Ciara Murphy, and is working on nano-engineered biomaterials for bone treatment. Before it, she was a postdoctoral researcher in the research group of Professor Saurabh Ghosh at IIT Delhi. Dr. Kulvinder has many fellowships and awards to her name. Some of them are Government of Ireland Postdoctoral Fellowship, Marie Curie Individual Fellowship, Crateman Postdoc Fellowship, Inspire Fellowship. She is a member of many professional bodies like Orthopedic Research Society, Tissue Engineering and Regenerative Medical International Society European Chapter, Controlled Release Society, Society for Biomaterials and Artificial Organs. She is a guest editor to MDPI Journal Pharmaceutical. She is a reviewer to many journals. Few of them are Material Science and Engineering C, Journal of Non-Crystalline Solids, Journal of Material Science, ACS Biomaterial Science and Engineering, Radiation Physics and Chemistry, MDPI Journal GEL. Now I request Dr. Kulvinder Kaur to please deliver her today's talk.
Shall I start? Good afternoon, everyone, and thanks for the kind introduction. Rajan sir is my senior. Professor Goel is also my senior from the same institute. So as he introduced, like today I'm presenting about what we are doing at Ireland and what I have did in my PhD at Guru Nanak Dev University, Amritsar. But before going forward, briefly, I wanna introduce what I did, especially इसलिए कि क्योंकि बहुत सारे बच्चे थे पिंडां वाले स्कूलों चों आए होने हैं जेडे मास्टर्स कर रहे हैं ਤੇ ਮੈਂ ਕੋਸ਼ਿਸ਼ ਕਰੂੰਗੀ ਕਿ ਆਪਣੀ ਪ੍ਰੈਜੈਂਟੇਸ਼ਨ ਨੂੰ ਬਹੁਤ ਸਿੰਪਲ ਰੱਖਾਂ ਤਾਂ ਕਿ ਸਾਰਿਆਂ ਨੂੰ ਸਮਝ ਆ ਸਕੇ ਤੇ ਜੇ ਮੈਂ ਕਰ ਸਕਦੀ ਹਾਂ ਤੇ ਕੋਈ ਵੀ ਬੱਚਾ ਕਰ ਸਕਦਾ ਹੈ, ਇਹ ਕੋਈ ਔਖੀ ਗੱਲ ਨਹੀਂ ਹੈ। ਮੈਂ ਆਪਣੀ 10th ਪਾਸ ਕੀਤੀ ਸੀ ਆਪਣੇ ਪਿੰਡ ਦੇ ਸਕੂਲ ਚੋਂ। ਮੇਰਾ ਪਿੰਡ ਹੈ ਜ਼ਿਲ੍ਹਾ ਫਿਰੋਜ਼ਪੁਰ ਦੇ ਵਿੱਚ ਕੌਰ ਸਿੰਘ ਵਾਲਾ, ਤੇ ਮੇਰਾ 10th ਤੱਕ ਪੰਜਾਬੀ ਮੀਡੀਅਮ ਸੀ। +1 ਚ ਜਾ ਕੇ ਮੈਂ ਇੰਗਲਿਸ਼ ਮੀਡੀਅਮ ਅਡਾਪਟ ਕੀਤਾ ਸੀ। ਸੋ ਜੇ ਕੋਈ ਬੱਚਾ ਇੱਥੇ ਬੈਠਾ ਹੋਏ ਸੋਚ ਰਿਹਾ ਹੈ ਕਿ ਮੇਰੀ ਇੰਗਲਿਸ਼ ਅੱਛੀ ਨਹੀਂ ਹੈ, ਮੈਂ ਪੰਜਾਬੀ ਬੈਕਗ੍ਰਾਉਂਡ ਤੋਂ ਆਇਆ, ਇਟਸ ਨਾਟ ਅ ਬਿਗ ਇਸ਼ੂ, ਯੂ ਕੈਨ ਡੂ ਐਨੀਥਿੰਗ ਇਫ ਯੂ ਹੈਵ ਅ ਡਿਟਰਮੀਨੇਸ਼ਨ ਟੂ ਡੂ ਦੈਟ। After doing my 10th, I did my BSc from Government Barjindra College, Faridkot in non-medical. And after completing my bachelor's, I want to do master's from a university because I want to go in research in future. Because at that time in my mindset was like, I want to do a permanent job in India, in Punjab. I want to become a teacher. At that time, I want to become a school teacher. So I adopt Guru Nanak Dev University because according to the budget constraints and my family issues, I goes to GNDU for doing my master's in applied physics. And in my master's, I secured first rank. And when you got first position in university, you get Inspire Fellowship from DST India, which is still going on. So after getting Inspire Fellowship, I joined PhD in 2012 with Dr. KJ Singh on bioactive glasses. So as Professor Goel explained, the role of glasses in nuclear waste, like this is the beauty of science, like the same material you can use in different applications. I am using bioactive glasses, or you can term as glasses for human health. So after completing my PhD, I submit my thesis in August 2017, and I joined IIT Delhi as a postdoc with Professor Saurabh Ghosh. And while I was doing a postdoc at IIT Delhi, I want to go abroad for international experience because at that time my mindset was that if I got an international experience, I will get a better job in India. But now it's totally changed because with time you evaluate yourself. So while I was doing my postdoc at IIT Delhi, I try applying for postdoc position, and every time I got rejection. If I directly apply, like we don't have funds because I was from Punjab University, like a normal University of Punjab. If you have a like tag of IIT or ICER, then you will get selected easily. So I got rejection many times. Then I decided to go with my own funds. So I try applying for the different fellowships, and I got rejected from Banting Postdoctoral Fellowship, which is a Canadian fellowship. So because I'm showing only which I have successful, but every successful story have a multiple unsuccessful stories. So I got two, one from the government of Israel, which is Greteman Postdoctoral Fellowship, and second I got government of Ireland Postdoctoral Fellowship. Then I talked with my both supervisors, and they like advise me that Ireland is a better position to go because I have a more facilities if I move to Ireland. So in 2020, before COVID pandemic, I moved to Ireland in January 2020, and I started working as IRC Postdoctoral Fellowship at Royal College of Surgeons in Ireland. And when I was moved there, then I come to know about the Marie Curie Fellowship. And in Marie Curie Fellowship, this is the limitation that if you are staying in a same country for 1 year, then you are not eligible from that country. You have to move to another country. So when I was there in 2020, me and my supervisor decided that this is the best option. We should go for this fellowship first year. So we applied in 2020, and luckily I got, not working. Yeah, thank you. I got individual fellowship from European Commission, and now from this January, I start working as a Marie Curie postdoctoral fellowship. So now briefly about my work, where it all began. You know, when we have a fracture or we have a bone defect, we go to the orthopedician, and what they suggested that you should go for an implant. Like my mother had a hairline fracture in her leg, but she's 60 plus. So when we moved to orthopedician, they suggested that due to age, it will not be repaired. It will take time. So she should go for the implant. And she has an implant in her leg, which is a titanium aluminum alloy. And the second option is we can take a graft from another person or from the same person or from different species. Like in bone grafting, we have option like autograft. I think it's not working. Yeah, autograft in which we take the graft from the same person. Like जिस person ਦੇ defect है उसे ही person ਦੀ body ਦੇ ਕਿਸੇ ਹੋਰ part ਤੋਂ mass ਲੈ ਕੇ ਉਸ ਜਗ੍ਹਾ ਤੇ implant ਕਰ ਦਿੰਦੇ ਆ ਜਿਸ ਜਗ੍ਹਾ ਤੇ bone defect ਹੋਇਆ ਹੁੰਦਾ। ਸੈਕਿੰਡ ਆਪਸ਼ਨ ਕੀ ਹੁੰਦੀ ਹੈ ਕਿ ਜਿਵੇਂ ਕੋਈ ਡੋਨਰ ਹੈ ਸੇਮ ਫੈਮਿਲੀ ਤੋਂ ਹੋ ਸਕਦਾ ਹੈ, ਜਿਸ ਦੀ ਉਸਦੇ ਬਲੱਡ ਕੰਪੈਟੀਬਿਲਿਟੀ ਸਾਰਾ ਕੁਝ ਮੈਚ ਕਰਦਾ ਹੈ, ਉਹ ਕਰਦਾ ਉਹਦੇ ਤੋਂ ਤੁਸੀਂ ਲੈ ਸਕਦੇ ਹੋ। ਥਰਡ ਹੈ ਜੀਨੋਗ੍ਰਾਫਟ, ਜਿਹਦੇ ਵਿੱਚ ਡਿਫਰੈਂਟ ਸਪੀਸੀਜ਼ ਦੇ ਵਿੱਚੋਂ ਉਹ ਜਿਹੜਾ ਹੈ ਗ੍ਰਾਫਟ ਲੈ ਕੇ ਜਿਸ ਪਰਸਨ ਦੇ ਡਿਫੈਕਟ ਹੁੰਦਾ ਉਸ ਦੇ ਵਿੱਚ ਇੰਪਲਾਂਟ ਕਰਦੇ ਆ। ਇਹਨਾਂ ਨੂੰ ਬੋਲਦੇ ਆ ਅਸੀਂ 골ਡ ਸਟੈਂਡਰਡ ਫॉर ਬੋਨ ਗ੍ਰਾਫਟਿੰਗ, ਜਿਹਦੇ ਵਿੱਚ ਆਟੋਗ੍ਰਾਫਟਸ ਐਂਡ ਐਲੋਗ੍ਰਾਫਟ ਆਉਂਦੇ ਆ, ਬਟ ਦੇ ਹੈਵ ਸਮ ਕੰਪਲੀਕੇਸ਼ਨ। ਸਪੋਜ਼ ਜਿਸ ਪਰਸਨ ਤੋਂ ਤੁਸੀਂ ਗ੍ਰਾਫਟਿੰਗ ਲੈ ਰਹੇ ਹੋ ਉਸਨੂੰ ਕੋਈ ਡਿਸੀਜ਼ ਹੈ ਜਿਸ ਦਾ ਉਸਨੂੰ ਵੀ ਨਹੀਂ ਪਤਾ, ਉਹ ਤੁਹਾਡੀ ਬਾਡੀ ਦੇ ਵਿੱਚ ਟ੍ਰਾਂਸਫਰ ਹੋ ਜਾਏਗਾ। ਦੂਸਰਾ ਸਾਡੇ ਕੋਲ ਕੀ ਹੁੰਦਾ ਹੈ ਕਿ ਇਨਸਫੀਸ਼ੀਐਂਟ ਟਿਸ਼ੂ, ਜਿੰਨਾ ਡਿਫੈਕਟ ਹੋ ਰਿਹਾ ਹੈ ਉਹਨੇ ਸਾਡੇ ਕੋਲ ਡੋਨਰਸ ਜਾਂ ਪਰਸਨ ਅਵੇਲੇਬਲ ਨਹੀਂ ਹੁੰਦੇ। ਸੈਕਿੰਡ ਕੀ ਹੈ ਕਿ ਇਮਿਊਨਿਟੀ ਸਿਸਟਮ, ਹੁਣ ਕੋਵਿਡ ਤੋਂ ਬਾਅਦ ਸਭ ਨੂੰ ਪਤਾ ਚੱਲ ਗਿਆ ਹੋਣਾ ਕਿ ਇਮਿਊਨਿਟੀ ਕਿੰਨੀ ਇੰਪੋਰਟੈਂਟ ਹੈ। ਇਮਿਊਨਿਟੀ ਵਿਟਾਮਿਨ ਸੀ ਸਭ ਨੇ ਸੁਣ ਲਿਆ ਹੋਣਾ। ਸੋ ਹਰ ਪਰਸਨ ਦੀ ਇਮਿਊਨਿਟੀ ਜਿਹੜੀ ਆ ਉਹ ਡਿਫਰੈਂਟ ਹੁੰਦੀ ਹੈ। ਜਦੋਂ ਤੁਸੀਂ ਉਸ ਤੋਂ ਡੋਨਰ ਤੋਂ ਲੈ ਕੇ ਕਿਸੇ ਵਿੱਚ ਇੰਪਲਾਂਟ ਕਰਦੇ ਹੋ ਤਾਂ ਇਮਿਊਨਿਟੀ ਦਾ ਫੈਕਟਰ ਜਿਹੜਾ ਉਹ ਬਹੁਤ ਕ੍ਰਿਟੀਕਲ ਰੋਲ ਪਲੇ ਕਰਦਾ ਹੈ। ਫਿਰ ਉਸ ਤੋਂ ਬਾਅਦ ਇਸ ਸਭ ਨੂੰ ਓਵਰਕਮ ਕਰਨ ਦੇ ਲਈ ਬਾਇਓ ਮਟੀਰੀਅਲਸ ਜਿਹੜੇ ਆ 골ਡ ਸਟੈਂਡਰਡ ਦੇ ਰੂਪ ਦੇ ਵਿੱਚ ਸਾਹਮਣੇ ਆਏ। ਬਾਇਓ ਮਟੀਰੀਅਲਸ ਕੀ ਹੈ, ਉਸ ਵਿੱਚ ਜਿਵੇਂ ਪ੍ਰੋਫੈਸਰ ਗੋਇਲ ਨੇ ਡਿਸਕਸ ਕੀਤਾ ਉਹ ਗਲਾਸ ਵੀ ਹੋ ਸਕਦੇ ਆ। ਬਾਇਓ ਮਟੀਰੀਅਲ ਇਜ਼ ਅ ਮਟੀਰੀਅਲ ਵਿਚ ਇਜ਼ ਬਾਇਓ ਕੰਪੈਟੀਬਲ। ਓਕੇ, ਸੋ ਇਹਦੇ ਵਿੱਚ ਸਾਡੇ ਕੋਲ ਸਿਰੇਮਿਕਸ ਹੋ ਸਕਦੇ ਆ, ਗਲਾਸ ਹੋ ਸਕਦੇ ਆ। ਸਿਰੇਮਿਕਸ ਬੋਲਦੇ ਆ ਜਿਹੜੇ ਕ੍ਰਿਸਟਲਾਈਨ ਮਟੀਰੀਅਲਸ ਹੁੰਦੇ ਆ ਜਾਂ ਸੈਮੀ ਕ੍ਰਿਸਟਲਾਈਨ ਮਟੀਰੀਅਲ, ਐਂਡ ਗਲਾਸ ਵਿਲ ਬੀ ਅਮੋਰਫਸ। ਸੋ ਇਹਦੇ ਵਿੱਚ ਕੈਲਸ਼ੀਅਮ ਫਾਸਫੇਟ ਆ ਸਕਦਾ ਹੈ, ਸਿਲੀਕੇਟ ਆ ਸਕਦਾ ਹੈ, ਦੈਨ ਪੋਲੀਮਰਸ ਜਿਹਦੇ ਵਿੱਚ ਨੈਚੁਰਲ ਪੋਲੀਮਰਸ ਆ ਸਕਦੇ ਆ, ਜਿਵੇਂ ਕੋਲੇਜਨ ਸਾਡੀ ਬਾਡੀ ਦਾ ਬਹੁਤ ਇੰਪੋਰਟੈਂਟ ਪਾਰਟ ਹੈ, ਕੋਲੇਜਨ ਆ ਸਕਦਾ, ਜਾਂ ਸਿੰਥੈਟਿਕ ਪੋਲੀਮਰਸ ਆ ਸਕਦੇ ਆ ਜਿਵੇਂ PMMA ਜਿਹੜਾ ਪੋਲੀਮਿਥਾਈਲ ਮੈਥਾਕ੍ਰਾਈਲੇਟ, ਇਟਸ ਕਾਲਡ ਅ ਬੋਨ ਸੀਮੈਂਟ। ਜਦੋਂ ਵੀ ਕਿਸੇ ਨੂੰ ਹਿਪ ਫ੍ਰੈਕਚਰਸ ਹੁੰਦਾ ਹੈ ਤਾਂ ਉਹਦੇ ਵਿੱਚੋਂ ਬੋਨ ਸੀਮੈਂਟ ਜਿਹੜਾ ਉਹ ਇੰਜੈਕਟ ਕਰਦੇ ਆ। ਉਸ ਤੋਂ ਬਾਅਦ ਕੰਪੋਜ਼ਿਟਸ ਆ ਸਕਦੇ ਆ ਜਿਹਦੇ ਵਿੱਚ ਤੁਸੀਂ ਗਲਾਸ ਤੇ ਪੋਲੀਮਰਸ ਨੂੰ ਮਿਕਸ ਕਰਦੇ ਹੋ ਤੇ ਉਸ ਨੂੰ ਇੰਪਲਾਂਟ ਵਾਲੀ ਜਗ੍ਹਾ ਤੇ ਜਿੱਥੇ ਵੀ ਡਿਫੈਕਟ ਹੈ ਉੱਥੇ ਇੰਪਲਾਂਟ ਕਰਦੇ ਹੋ। ਐਂਡ ਥਰਡ ਕਮਰਸ਼ੀਅਲੀ ਅਵੇਲੇਬਲ ਵੀ ਮਟੀਰੀਅਲ ਹੈਗੇ ਆ ਜਿਹੜੇ ਡਾਕਟਰਸ ਜਿਹੜੇ ਯੂਜ਼ ਕਰਦੇ ਆ, ਜਿਹਦੇ ਵਿੱਚ ਹੈਗਾ ਮੈਡਟ੍ਰੋਨਿਕਸ ਦਾ ਇਨਫਿਊਜ਼। ਇਹ ਜਿਹੜਾ ਹੈ ਕਮਰਸ਼ੀਅਲੀ ਅਵੇਲੇਬਲ ਮਟੀਰੀਅਲ ਆ, ਬਟ ਪ੍ਰੋਬਲਮ ਕੀ ਹੈ ਕਿ ਜਿਹੜੇ ਕਮਰਸ਼ੀਅਲੀ ਅਵੇਲੇਬਲ ਆ ਜਦੋਂ ਕੋਈ ਮੈਟਾਬੋਲਿਕ ਬੋਨ ਡਿਸੀਜ਼ ਹੁੰਦੀ ਹੈ ਜਿਹੜੀ ਕਿ ਜੋ ਵੀ ਸਾਇਲੈਂਟ ਡਿਸੀਜ਼ ਹੁੰਦੀ ਹੈ ਉਸ ਦੇ ਵਿੱਚ ਅਸੀਂ ਇਸ ਨੂੰ ਯੂਜ਼ ਨਹੀਂ ਕਰ ਸਕਦੇ। ਸੋ here are some clinical applications of biomaterials ਜਿਹੜੀ ਅਸੀਂ different ਜਦੋਂ ਵੀ ਕੋਈ joint defect ਹੈ ਉਹਦੇ ਵਿੱਚ there are different types of biomaterials, bioglasses, ceramics are used in different parts of human body. So ਜਦੋਂ ਵੀ ਅਸੀਂ ਕਿਸੇ ਬਾਇਓਮਟੀਰੀਅਲ ਦੀ ਸਿੰਥੇਸਿਸ ਦੇ ਲਈ ਕੋਈ ਵੀ ਐਲੀਮੈਂਟਲ ਕੰਪੋਜੀਸ਼ਨ ਸਿਲੈਕਟ ਕਰਦੇ ਹਾਂ, ਜਿਵੇਂ ਹੁਣੇ ਪ੍ਰੋਫੈਸਰ ਗੋਇਲ ਨੇ ਦੱਸਿਆ ਕਿ ਅਸੀਂ ਸੋਡੀਅਮ ਜਿਹੜਾ ਹੈ ਪੀਰੀਓਡਿਕ ਟੇਬਲ ਦੇ ਵਿੱਚ ਕਿਹੜੇ ਨਿਊਕਲੀਅਰ ਵੇਸਟ ਦੇ ਵਿੱਚ ਆਉਂਦੇ ਆ। ਸੋ ਇਹ ਮਟੀਰੀਅਲਸ ਜਿਹੜੇ ਆ ਆਇਨਸ ਆ ਬਿਕੋਜ਼ ਦੇ ਆਰ ਬੈਨੀਫੀਸ਼ੀਅਲ ਫॉर ਐਵਰੀ ਪਰਪਸ। ਸੋ ਇਹ ਤਾਂ ਸਭ ਨੂੰ ਪਤਾ ਹੋਣਾ ਹੈ ਕਿ ਜਦੋਂ ਬਲੱਡ ਪ੍ਰੈਸ਼ਰ ਜਿਹੜਾ ਹੈ ਉਹ ਲੋ ਹੁੰਦਾ ਹੈ ਤਾਂ ਅਸੀਂ ਲਿਮਕਾ ਪੀਂਦੇ ਆ ਜਾਂ ਕਹਿੰਦੇ ਆ ਕਿ ਨਿੰਬੂ ਵਾਲਾ ਪਾਣੀ ਪੀਓ, ਕਿਉਂਕਿ ਨਮਕ ਵਾਲੇ ਪਾਣੀ ਦੇ ਵਿੱਚ ਸੋਡੀਅਮ ਕਲੋਰਾਈਡ ਹੁੰਦਾ ਹੈ ਤਾਂ ਸਾਡੇ ਬਲੱਡ ਪ੍ਰੈਸ਼ਰ ਨੂੰ ਰੈਗੂਲੇਟ ਕਰ ਦਿੰਦਾ ਹੈ। ਸੋ ਇਸੇ ਤਰ੍ਹਾਂ ਜਦੋਂ ਵੀ ਅਸੀਂ ਬਾਇਓਮਟੀਰੀਅਲ ਦੀ ਕੋਈ ਵੀ ਕੰਪੋਜੀਸ਼ਨ ਸਿਲੈਕਟ ਕਰਦੇ ਹਾਂ ਅਸੀਂ ਪਹਿਲਾਂ ਇਹ ਦੇਖਦੇ ਹਾਂ ਕਿ ਉਹ ਜਿਹੜਾ ਆਇਨ ਹੈ ਉਹ ਬਾਡੀ ਦੇ ਲਈ ਬੈਨੀਫੀਸ਼ੀਅਲ ਹੈ, ਉਸਦਾ ਕੋਈ ਟੌਕਸਿਕ ਇਫੈਕਟ ਨਹੀਂ ਆਉਣਾ ਚਾਹੀਦਾ ਕਿਉਂਕਿ ਬਾਡੀ ਦੇ ਅੰਦਰ ਉਸਨੇ ਜਾਣਾ ਹੁੰਦਾ ਹੈ। So these are few examples like calcium ਜਿਹੜਾ ਉਹ healthy bones ਦੇ ਲਈ ਹੁੰਦਾ ਹੈ, ਸਭ ਨੂੰ ਪਤਾ ਹੈ, teeth ਦੇ ਲਈ ਹੁੰਦਾ ਹੈ। ਸੋ ਇਸ ਤਰ੍ਹਾਂ ਅਸੀਂ ਜਿਹੜੇ ਜਦੋਂ ਬਾਇਓਮਟੀਰੀਅਲ ਦੀ ਸਿੰਥੇਸਿਸ ਕਰਦੇ ਹਾਂ ਅਸੀਂ ਮਟੀਰੀਅਲਸ ਅਕੋਰਡਿੰਗ ਟੂ ਬਾਡੀ ਕੰਪੋਜੀਸ਼ਨ ਸਿਲੈਕਟ ਕਰਦੇ ਹਾਂ। ਫਿਰ ਉਸ ਤੋਂ ਬਾਅਦ ਜਦੋਂ ਸਾਡਾ ਬਾਇਓਮਟੀਰੀਅਲ ਅਸੀਂ ਲੈਬ ਦੇ ਵਿੱਚ ਸਿੰਥੇਸਿਸ ਕਰ ਲਿਆ, ਸਾਡਾ ਫਰਸਟ ਸਟੈਪ ਕੀ ਹੁੰਦਾ ਹੈ ਕਿ ਅਸੀਂ ਉਹਦੀ ਇਨ ਵਿਟਰੋ ਬਾਇਓ ਐਕਟੀਵਿਟੀ ਚੈੱਕ ਕਰਨੀ ਹੈ ਕਿ ਉਹ ਬਾਇਓ ਕੰਪੈਟੀਬਲ ਹੈ ਜਾਂ ਨਹੀਂ ਹੈ। ਉਹਦੇ ਲਈ ਅਸੀਂ ਬਣਾਉਂਦੇ ਹਾਂ ਸਿਮੂਲੇਟਡ ਬਾਡੀ ਫਲੂਇਡ। ਸਿਮੂਲੇਟਡ ਬਾਡੀ ਫਲੂਇਡ ਜਿਹੜਾ ਹੈ ਉਸਦੀ ਆਇਨਿਕ ਕੰਸੈਂਟ੍ਰੇਸ਼ਨ ਇਕੁਇਵਲੈਂਟ ਟੂ ਅ ਹਿਊਮਨ ਬਲੱਡ ਪਲਾਜ਼ਮਾ। ਕੁਕੂਬੋ ਇੱਕ ਸਾਇੰਟਿਸਟ ਸੀ ਜਿਸਨੇ ਇਸ ਦੀ ਕੰਪੋਜੀਸ਼ਨ ਦਿੱਤੀ ਸੀ ਕਿ ਇਸ ਨੂੰ ਕਿਵੇਂ ਬਣਾ ਸਕਦੇ ਹਾਂ ਲੈਬ ਦੇ ਵਿੱਚ, ਤੇ ਉਸਦੀ ਜਿਹੜੀ ਰੈਸਿਪੀ ਆ ਉਹੀ ਸਾਰੇ ਸਾਇੰਟਿਸਟ ਫੋਲੋ ਕਰਦੇ ਆ। ਇਸ ਨੂੰ ਅਸੀਂ ਬਣਾਉਣੇ, ਇਸ ਦੀ ਇਕੁਇਵਲੈਂਟ ਹੁੰਦੀ ਹੈ ਹਿਊਮਨ ਬਲੱਡ ਪਲਾਜ਼ਮਾ ਦੇ। ਉਸ ਤੋਂ ਬਾਅਦ ਕੀ ਕਰਦੇ ਹਾਂ ਅਸੀਂ ਬਾਇਓਮਟੀਰੀਅਲ ਬਣਾ ਲਿਆ, ਉਸ ਤੋਂ ਬਾਅਦ SBF ਵੀ ਬਣਾ ਲਿਆ। ਉਸ ਤੋਂ ਬਾਅਦ ਅਸੀਂ particular ratio ਲੈਂਦੇ ਹਾਂ, suppose 1 gram of biomaterial in 25 ml of SBF solution। SBF solution ਦੇ ਵਿੱਚ ਅਸੀਂ ਸੈਂਪਲ ਰੱਖਤਾ। ਮੈਂ ਹੁਣੇ ਤੁਹਾਨੂੰ ਦੱਸਿਆ ਕਿ ਅਸੀਂ different ਜਿਹੜੇ ਆਇਨਸ ਹੈ ਕੰਪੋਜੀਸ਼ਨ ਦੇ ਉਹ ਸਿਲੈਕਟ ਕਰ ਲੈਂਦੇ ਹਾਂ। ਤੇ ਬਾਇਓਮਟੀਰੀਅਲ ਦੇ ਵਿੱਚ ਸਾਰੇ ਐਲੀਮੈਂਟਸ ਹੈਗੇ ਜਿਹੜੇ ਅਸੀਂ ਸਿਲੈਕਟ ਕੀਤੇ ਹੋਏ ਆ ਪੀਰੀਓਡਿਕ ਟੇਬਲ ਤੋਂ ਕਿ ਸਾਨੂੰ ਇਹ ਵਾਲਾ ਆਇਨ ਜਿਹੜਾ ਆਪਣੇ ਮਟੀਰੀਅਲ ਦੇ ਵਿੱਚ ਚਾਹੀਦਾ। ਜਦੋਂ ਇਹਨੂੰ SBF ਦੇ ਵਿੱਚ ਪਾਇਆ ਫਸਟ ਸਟੈਪ ਕੀ ਹੋਏਗਾ, ਜਿਹੜੇ ਆਇਨਸ ਆ ਉਹ ਲੀਚ ਆਊਟ ਹੋ ਜਾਣਗੇ ਕਿਉਂਕਿ ਬੌਂਡ ਬ੍ਰੇਕਿੰਗ ਹੋਏਗੀ। ਬੌਂਡ ਬ੍ਰੇਕਿੰਗ ਹੋਣ ਦੇ ਨਾਲ ਜਿਹੜੇ ਆਇਨਸ ਆ ਉਹ SBF ਦੇ ਨਾਲ ਤੇ ਹਿਊਮਨ ਬਲੱਡ ਪਲਾਜ਼ਮਾ ਦੀ ਜਿਹੜੀ ਰੇਸ਼ੀਓ ਉਹਦੇ ਨਾਲ ਐਕਸਚੇਂਜ ਹੋਣਗੇ। ਐਕਸਚੇਂਜ ਹੋਣ ਤੋਂ ਬਾਅਦ ਕੀ ਹੋਏਗਾ ਕਿ ਸੋਡੀਅਮ ਜਿਵੇਂ ਸੀਗਾ ਸਾਡੇ ਮਟੀਰੀਅਲ ਦੇ ਵਿੱਚੋਂ ਬਾਹਰ ਨਿਕਲ ਗਿਆ, ਸਾਡੇ ਕੋਲ ਕੀ ਬਚ ਗਿਆ SiOH ਜਿਹਨੂੰ ਬੋਲਦੇ ਸਿਲੇਨੋਲ। ਹੁਣੇ ਆਸ਼ੂਤੋਸ਼ ਸਰ ਨੇ ਵੀ ਤੁਹਾਨੂੰ ਐਕਸਪਲੇਨ ਕੀਤਾ ਸੀ ਇੱਕ ਡਾਇਗਰਾਮ ਦੇ ਵਿੱਚ ਕਿ ਫਸਟ ਸਟੈਪ ਦੇ ਵਿੱਚ ਕੀ ਹੁੰਦਾ ਹੈ, ਸੈਕੰਡ ਸਟੈਪ ਦੇ ਵਿੱਚ ਕੀ ਹੁੰਦਾ ਹੈ। ਫਿਰ ਨੈਕਸਟ ਕੀ ਹੋਏਗਾ, ਨੈਕਸਟ ਸਾਡਾ ਜਿਹੜਾ SiO ਗਰੁੱਪ ਹੈ ਉਹ ਇੱਕ ਸਿਲੇਨੋਨ ਲੇਅਰ ਬਣਾਏਗਾ ਜਿਸ ਨੂੰ ਬੋਲਦੇ ਆ ਹਾਈਡਰੇਟਡ ਸਿਲਿਕਾ ਲੇਅਰ। This hydrated silica layer act as a nucleation site for the deposition of calcium and phosphorus ion on the surface of these silanol layer. ਇਸ silanol layer ਦੇ ਉੱਪਰ calcium and phosphorus ion ਜਿਹੜੇ ਆ ਉਹ solution ਦੇ ਵਿੱਚੋਂ deposit ਹੋਣਾ ਸ਼ੁਰੂ ਹੋ ਜਾਂਦੇ ਆ। ਜਦੋਂ ਇਹਨਾਂ ਦੀ deposition complete ਹੋ ਜਾਂਦੀ, ਇਹ ਮਿਲ ਕੇ ਬਣਾਉਂਦੇ ਆ hydroxyl apatite, which is called synthetic bone. ਜੇ ਸਾਡੇ material ਇਹ ਵਾਲੇ ਸਾਰੇ ਸਟੈਪ ਪਾਸ ਕਰਕੇ ਹਾਈਡਰੋਕਸਿਲ ਐਪੇਟਾਈਟ ਲੇਅਰ ਬਣਾ ਲੈਂਦਾ ਹੈ ਤਾਂ ਅਸੀਂ ਉਸ ਨੂੰ ਕਹਿੰਦੇ ਆ ਕਿ ਸਾਡਾ ਮਟੀਰੀਅਲ ਬਾਇਓਐਕਟਿਵ ਹੈ। So this is the first step to judge in a lab that the material you have synthesized is bioactive or not. This is like a layman definition of what is biomaterial. So after that, to show how if we have a bone defect, then we implant, then how it actually happens in the human body. So briefly about my PhD work, I work on bioglass and bioceramics based scaffolds for bone tissue engineering, in which I study the effect of particle size, ions and bone cell activity and microorganisms. And then I prepared mechanically robust PMMA, PBS, TCU is a polyester, and hydroxyapatite scaffolds, then prepare fluorescent probes, because when we implant our material in the body, then we want to track like where it is at current position. So we need some fluorescent ligands on the surface of the biomaterials. Then I prepare anti-osteoporotic agents. And then what we do SEM to study what is the structural of our biomaterial. It's a needle shape, it's a spherical, because shape is also affect the bone morphology, bone cell activity and everything. Then we do H&E staining to check like, is there any bone formation or not after the cell culture. I will explain it later. And then we, as I explained earlier, you can see in the left side of XRD graph, it's XRD graph to identify, is there any hydroxyapatite formation on the surface of the material or not. You can see before, after 1 day, after 5 days, after 12 days, it's in SPF. Before is like what I prepare in the lab, and after 1 day is the XRD of the sample, after 1 day in SBF. Is there any structural change? Is there any ion release? What is the effect? It's bioactive. And if you get the peak at 31.8, which is the fingerprint peak of hydroxyapatite, it means the sample is going to produce hydroxyapatite on the surface of the sample. And then from SEM and EDX, I don't know how many PhD students are here. If you know, like in EDX, we can find out the concentration of different ions, like how much calcium in your sample, how much phosphorus in your sample, before and after. You can see like calcium and phosphorus concentration increased to 400, and before it was like below 100. So calcium and phosphorus start deposition on the surface of the sample. And third, we also check the antibacterial effect, because at the end, this material will go into the body. And if it has immune response, like body will not take as its own part. So we check its antibacterial effect with different microorganisms. Here I'm showing with the MRSA, which is the most resistant strain for any drug. So you can see these black circles. This means my material is like inhibiting the growth of bacteria and this range. So we all check these parameters. So then I did the in vivo study in the 36 female rats. First, we induce osteoporosis. Osteoporosis is the silent disease. You come to know about this disease when you have a bone fracture. Basically, with advancing age, your bones become so fragile that you don't even know that the bone density is reduced. When you go for your calcium phosphate test, then you came to know like, okay, my bone density is decreased. That's why you have a pain in the back, or your spinal cord is tilted like that. So we did with the dexamethasone, which is a steroid. So we induced osteoporosis in the rats. And then we did give the doses which we prepared in the lab, like micron hydroxyapatite and nano hydroxyapatite. And we found that with nano hydroxyapatite, we have a higher bone density as compared to micron size particle. So after this was my PhD work. And after completing my PhD, I moved to IIT Delhi with Professor Saurabh Ghosh, and there they said, because every lab have their different area of research, they said forget about powder materials because they work on 3D printing. They print patient-specific and defect-specific systems because we believe that, and it's true that in 3D printing, you can recapitulate the architectural complexity of the human bone. So here I 3D printed different structures of hydroxyapatite according to the defect site. What is the defect area, how much defect you have, how many centimeter. So here's the example. This was the salesman. Like this is the 3D model of the defect of a face of a person. In IIT Delhi, we have a patient, and he was the salesman due to the road accident. He have a maxillofacial defect, and we got the MRI scan of that person from AIIMS, and then we design a 3D model for that, and we measure the defect size. What is the defect size? Then we print different shapes of hydroxyapatite on 3D printing, and then we make a chain with PMMA because we use bone cement for the fixation, and then we implant at the trauma center at IIT Delhi with Professor Sujanta Mohanty. She is in stem cell research in AIIMS Delhi. And then after 3 years, we were taking care of that person, like he's like can speak well after the implantation, he can eat well. So everything was fine up to 3 years. So this was the first successful, which I seen with my eyes, like, okay, these biomaterials are actually helping the society. So after my IIT Delhi, I moved to Ireland in the group of Dr. Chiara Murphy. She's a young assistant professor and Department of Anatomy in RCSI, Royal College of Surgeons in Ireland. And here I work on injectable collagen-based hydrogels for osteoporosis treatment. So my main focus of research nowadays is osteoporosis treatment, because it's the most prevalent metabolic disease, and it happens when you have when there is a bone formation, there will be bone desorption. And when there is a higher bone desorption as compared to bone formation, then osteoporosis occurs. So but you can see from this, like it's normal bone, this is the osteoporotic bone, the bone becomes so fragile. But basically my focus is on osteoporotic vertebral fractures. ਅਸੀਂ ਕਹਿੰਦੇ ਰੀੜ ਦੀ ਹੱਡੀ, ਉਸਦੇ ਵਿੱਚ ਬੋਨਸ ਵੀ ਹੁੰਦਾ, ਉਹਦੇ ਵਿੱਚ ਸੌਫਟ ਟਿਸ਼ੂ ਵੀ ਹੁੰਦਾ। ਜਦੋਂ ਉਸ ਰੀੜ ਦੀ ਹੱਡੀ ਦੇ ਵਿੱਚ ਡਿਫੈਕਟ ਆਉਂਦਾ ਹੈ, what is the gold standard ਜਿਹੜੇ ਡਾਕਟਰ ਟ੍ਰੀਟਮੈਂਟ ਕਰਦੇ ਆ, they it's called vertebroplasty and kyphoplasty. What they do, they inject a bone cement at the defect side, but that bone cement is like a cement, very hard. When they inject that, after that the flexibility of the person can go forever. So, and the second option is when it's bone cement, you inject the bone cement is so hard that it can affect the other spinal cord. So you have a more problem like spinal cord damage like that. And the secondary fractures, which we call like the secondary fractures and cement leakage and adverse reaction to the bone cement, because sometimes body does not adopt it. So then what option we have? The biomaterials, but it also have some complex challenges. Like first thing, we need a higher mechanical strength, because this part is the most load bearing part of our body, because ਰੀੜ ਦੀ ਹੱਡੀ ਦੇ ਨਾਲ ਅਸੀਂ ਥੱਲੋਂ ਭਾਰ ਚੱਕਦੇ ਆਂ ਜਾਂ ਕੁਝ ਵੀ ਅਸੀਂ ਹੈਵੀ ਲਿਫਟ ਵਾਲਾ ਕਰਨਾ ਹੈ, ਉਹਦੇ ਲਈ ਸਾਡੀ ਸਪਾਈਨਲ ਕੋਰਡ ਦਾ ਸਟਰੋਂਗ ਹੋਣਾ ਬਹੁਤ ਜ਼ਰੂਰੀ ਹੈ। ਉਸ ਤੋਂ ਬਾਅਦ ਡਿਫਿਕਲਟੀ ਇਨ ਰਿਟੇਨਿੰਗ ਸੁਟੇਬਲ ਬਾਇਓਮਟੀਰੀਅਲ ਇਨ ਪਲੇਸ, ਕਿ ਤੁਸੀਂ ਜਿਸ ਜਗ੍ਹਾ ਤੇ ਬਾਇਓਮਟੀਰੀਅਲ ਨੂੰ ਫਿਕਸ ਕੀਤਾ ਉਸੇ ਜਗ੍ਹਾ ਤੇ ਹੀ ਰਵੇ, ਉਹ ਇੱਧਰ ਉੱਧਰ ਮੂਵ ਨਾ ਕਰੇ ਜਾਂ ਸੈਕੰਡਰੀ ਫ੍ਰੈਕਚਰਸ ਨਾ ਹੋਣ। Third, which I explained earlier, like risk of spinal cord damage with implantation and impaired bone remodeling. Like market ਦੇ ਵਿੱਚ osteoporosis ਦੀਆਂ drugs ਹੈ, which is called strontium ranolate, ਅਸੀਂ ਟੇਬਲੇਟ ਲੈਣੇ ਆ, ਡਾਕਟਰਸ ਦਿੰਦੇ ਵੀ ਆ ਪੰਜਾਬ ਦੇ ਵਿੱਚ ਵੀ। ਪਰ ਕੀ ਪ੍ਰੋਬਲਮ ਹੈ ਕਿ ਉਹ ਸਿਰਫ ਔਰ ਸਿਰਫ ਫਰਦਰ osteoporosis ਨੂੰ ਰੋਕ ਸਕਦਾ ਹੈ, ਪਰ ਜੋ ਪਹਿਲਾਂ ਡੈਮੇਜ ਹੋ ਚੁੱਕਿਆ ਉਸ ਨੂੰ ਉਹ ਰਿਪੇਅਰ ਨਹੀਂ ਕਰੂਗਾ, which is called impaired bone remodeling. So main aim of my research is to develop thermoresponsive. Thermoresponsive means it should be a solution at room temperature, but when it goes to 37 degrees, it should gel. It's called thermoresponsive, like temperature responsive, so that we can inject it with injection. The person does not need a surgery to go for that. And injectable means injection. Biomaterial with improved mechanical function means its mechanical strength should be higher enough that our body can work normally after that. And therapeutic properties. Therapeutic properties means we add some ions from the periodic table, like we use in my first project, we use strontium because strontium has both these anti-osteoporotic effect to repair and restore bone function in an osteoporotic load-bearing environment. So for that, in my first IRC fellowship, which we select, we use single wall carbon nanotubes as a mechanically filler, because you all know which work in physics, the single wall carbon nanotubes have a high mechanical strength. We don't use pristine ones because FDA does not approve. And if you are using any material in biomaterials, it should be approved by FDA. Then after you can think about like, okay, it will go into the human implantation or anything. So we use functionalized single wall carbon nanotubes, which were like approved by FDA. Then we prepare a thermoresponsive collagen chitosan hydrogels. You can see in the figures on the left side, before gelation, it was like a liquid, but when it moved to 37 degree, it become gel. And then these graphs are from the rheometer. This is a technique to investigate what is the gelation temperature of a material. And you can see it's called the storage modulus, which is like the mechanical properties of a gel. And loss modulus is also like how much, maybe who study the physics, like what Young's modulus and storage modulus and loss modulus, these are the same, the mechanical properties. You can say around 37, loss modulus decrease, but Young's modulus increase. It means the solution is turning into the gelation around the 37 degree. So next, after preparing this thermoresponsive materials, what we do, we check its weight loss, how it is behaving in SBF and everything. And the most importantly, we were interested into the mechanical strength, and we found that as we add the single wall carbon nanotubes into the collagen chitosan hydrogel, its Young modulus increased by 63%, which was equivalent to the human bone. So we were happy with the mechanical properties. We were happy with the thermoresponsive behavior. Then we move with the bioactivity properties in SBF, and then we check with the cells. We have two types of cells, mainly three types of cells, which we use in our lab. One we purchase, which are commercially available, which is called cell line. And secondly, we derived cells from the rats, which we call rat MSCs. And third, we take from because we are working in collaboration with the hospitals, so we take the cells from the humans. So we have different types of cells, but here I use bone cells. So then we check its DNA content, like the cells proliferate with my material or not. What was the toxicity of LDH is for the toxicity of the material. And then this was the first part of my project to optimize the thermoresponsivity, mechanical properties, and toxicity of the hydrogels. So in the next phase, we functionalized further single wall carbon nanotubes with the strontium hydroxyapatite, because we want to see the effect of therapeutic ions in the hydrogels, it is modified or not. Then we functionalize this. This is the structure of single wall carbon nanotube, which was carboxylic acid functionalized, and we further functionalize with strontium hydroxyapatite. And then we study TEM, SEM, and we found that we have like overlapped single wall carbon nanotubes with the strontium hydroxyapatite. And after that, we check its biocompatibility with the rat MSCs, and we found that these ALP, OCN, fold change, these are the PCR. The PCR test we do for the COVID test and something like that. So PCR we also do to check the gene expression of our cells, like how it's proliferating or down-regulating with our material. So I never did this before because I was from physics background. And in my PhD, this work was done by our collaborators, but my supervisor is very kind. She pushed me like, you should learn that. Then you have both the expertise. Like then I learned this, and I did this first time at Ireland. So then we check calcium deposition, how much calcium is depositing on our samples when we are working with the cells, and ALP like alkaline phosphatase, which is the early marker for bone regeneration. So we check early and late marker at different stages of bone formation. And then we also check the osteoclast. Osteoclasts are the cells for the bone resorption. So if your osteoblasts are proliferating, then osteoclast should be down-regulating. Then you have like not the impaired bone modeling, you have the proper bone remodeling. Then we check with the osteoclast, we use raw cells. This is called raw cells, which we have osteoclast. And we check that as we increase the concentration, this Cathepsin K, trap expression, these are all related to the osteoclast cells. Like if they down-regulate if you don't have a bone resorption. So The third was we did like antibacterial effect, as I explained earlier in my PhD, we did with the different strains. Same we did with our hydrogels. In PhD, we did powder samples. Here we did with the hydrogels, and we found that you can see this area. This means the bacteria is like our material is killing the bacteria at these sites. So after that, after when we were happy with our in vitro studies, these cells, this SPF, these structural properties, coating and everything, then we go for the animal model and we implanted it was black in color because single wall carbon nanotubes are black in color. So our material was black in color. So we implanted in the femoral defect of rats. And after 8 weeks, we get that there is a bone formation, bone density was improved and everything was okay. So for this work, we now got a feasibility grant from Enterprise Ireland. Enterprise Ireland is a government agency which gives funds for commercialization of biomaterials or any product you are preparing in the lab. It could be from physics, chemistry, or anything. First, they give you feasibility grant for 6 months, and you have to prove that, okay, my results are actually okay, but they need extra anything. After feasibility grant, they will give you commercialization grant. Then you can start your own company or you can partner with your industrial partners and you can set up a commercialization of your project. So this was my first fellowship, and now I'm working on my Marie Curie fellowship from January. And I have another supervisor in this, Dr. Aldo Boccaccini from Germany. I will prepare my bioglass in his lab. And what is the project is that we are preparing nano-engineering injectable biomaterials for osteoporotic bone treatment. And in Ireland, especially RCSI is obsessed with the fancy names. So we have a fancy name. And for this project, we have a nano boost. So what we are doing here, we are not tackling only the advancing age issue, which was in my previous project. Here we are dealing with the oxidative stress, which is induced by the reactive oxygen species with advancing age. So we will prepare the bioactive glasses by doping antioxidant ions from the periodic table, cerium, praseodymium, which are the rare earth elements, but they have antioxidant potential. So these glasses will be prepared with the collaboration with Professor Boccaccini, and then we will add this bioactive glass into the collagen hydrogels, and then we check what is the effect of ions and what is the effect of thermoresponsivity. And third thing we are using here, I forget to mention, is in spite of single wall carbon nanotubes, here we are using laponites, which is a 2D material from the clay family, and it has a high mechanical strength. So we are doping laponite, not the single wall carbon nanotubes in this project. So last, I want to share some opportunities in Ireland for master, for PhD, or for postdoc. If anyone is interested, for master's scholarship, you can apply Erasmus Mundus by European Commission. This is the fellowship for 2 years, and you can study your master in European countries, 3 different countries actually. Then you have a round, you can decide at the end in which country you want to settle down for your PhD or you want to move in another country. And if you are already in a master, and you have a vision like you want to do a research, then you can apply for the master internship program for 3 months, and you can come to any European country. And the third is the STAR program, which is especially by the RCSI, in which you can come to RCSI for 3 months, and they will pay you for your accommodation and 2,000 euro for 3 months for your expenses. And you can do your research with RCSI for 3 months. And if you have confusion like RCSI is a big, I don't know which supervisor I should go. So you can email the research office of our university or any university in which you want to go. They will guide you according to your background, according to your interest, which supervisor will be best suited for you. So research offices are very good. At least in RCSI, we have a very good research office. So you can talk to them if you have any confusion about that. And for PhD, STAR PhD is basically by RCSI, in which they select international students every year. Then UMBER is the Advanced Materials and Bioengineering Research Funding Agency, especially in Ireland. It gives funds for postdoc, for PhD. And then IRC, like Irish Research Council, this is the very good opportunity. Every year they select 300 international students, and you can apply for that. And it's very, very nice opportunity to join a PhD under RCSI, IRC funding. Then Health Research Board, then Science Foundation Ireland is the biggest funding agency in Ireland, and it gives like a very good amount of, I think the best fellowship is given by SFI in Ireland. Then Johnson & Johnson, you know, the company who prepared powders, talcum powders for kids, it also gives funds for to RCSI for PhD students. And at the time we have 3 Johnson & Johnson funded PhD students who are working with us, and PhD program like Marie Curie's for postdoc. Same, the European Commission give fellowship for Marie Curie for PhD students. And for postdoc, you can apply Government of Ireland. Every year they select 80 students outside Ireland, and then Marie Curie, obviously, and they also have a Marie Curie co-fund. Co-fund means half fund is given by European Commission and half fund is given by the funding agency of that country. Like in Ireland, we have 2, Umber and Curram. They fund a Marie Curie co-fund, and this Jurex Ireland is a website in which every scientific opening is published. So if you find any position at Jurex, that will be fully sure that you are going to the right place. You will get the hosting agreement, everything from there. And the third important thing which I want to mention, like the CV, which we prepare. Before that, it was the same for our country, but nowadays Ireland specifically, it started from the San Francisco, maybe Professor Goel about this DORA principles, because they think it started from San Francisco or Washington, I don't remember the exact location. They said like when we add impact factor, H-index, citations, the examiner become biased of the selection of candidates. So now for every funding agency in Ireland, they are following the DORA principle, in which you don't add your impact factor, H-index, you just add the impact of your publication, like in 3-4 lines, what you publish, what was that impact on social cause, basically they are interested into social economic impact, because it's all like taxpayers' money. They want to see what you have did. It's not like you published paper is 1,000 citation. They don't care about that now. They only care about what was the impact of your publication. So now when you submit any funding, you have to prepare your CV according to the DORA principles. Otherwise they reject your application. So just keep in mind if you want to apply in Ireland. So this was the important point. And this is my whole group. This is my supervisor and funding agencies. If you have any questions, you may ask me now, or otherwise you can email me anytime. And RCSI, or especially Ireland, is obsessed with Twitter. We use Twitter a lot. They don't like any other. So like they want us to publish and like tweet everything. So you can follow on Twitter and you can find everything. You can follow on Twitter the funding agencies, the institutes, they publish everything on Twitter, everything. They don't like any others, like LinkedIn or Google Scholar or anything. Just tweet, tweet, and tweet. So thank you so much.
Thank you, Dr. Kulvinder, for such a nice, detailed, and informative talk. And thank you for sharing this information regarding the research opportunities in Ireland. Now, dear participants, there will be a lunch break till 1:30, and we'll assemble together at 1:30 with our third speaker, Dr. Saurabh Kapoor, who is our industrial speaker and would shed light on the technological application of glasses. So let's assemble together at 1:30. Thank you so much for being with us.